Yes, so this third chapter, introducing chapter, I recall this was introduction for the course that will be in September. So essentially the result, but in some way it's good instead of taking a result from a black box to have some understanding what is inside the black box, even if you don't prove everything, but at least to have some feeling about it. This is the aim of those things. So this is devoted to Sieve. You know what is a sieve? A sieve is something with holes, and when you put your sand in it, the small parts go through and the larger part remain, according to whether you're interested in large parts or small parts. In any case, it's fine to have a sieve. So there are two books. I should have put it also in the list of the interesting books. One is really a very important one, Opera de Cribro. Cribro is the word for sieve in Italian or in Latin. In French it is crible. So Opera de Cribro, which is due to Iwaniec and Friedlander, Henryk Iwaniec and John Friedlander. And this appeared in AMS Colloquium series, number 57 in 2010. And really this is a very, very interesting. You have also some philosophy of Sieve at the different level, and you have nice results. Although you remember when we had this joint paper with Florian Luca and Yuri Bilou, if you want really to quote something precise, it may not be always the best thing to quote. And if you want to quote, it's more technical, but to quote it may be useful to have something from Heini Halberstam and Hans-Egon Richard. And this is Sieve methods. Academic Press, and this was in 1974, and there have been a lot of progress, of course, during this period. One of the main contributors being Iwaniec, but there have been a lot of other people contributing to that. So if you want really the latest things, maybe here, but useful to quote, maybe there. Okay. So we start with the first thing that I think everybody knows, which is the Sieve first section, the Sieve of Eratosthenes, and I will phrase it also in a slightly more modern way, and Legendre. So you all know how you can check whether a number is a prime. You check whether it is divisible by all the primes up to its square root. Okay? So this is the way you would do. And I don't know, I don't think there is anything to lose too much time on that. But let me write it in maybe a way which wouldn't have been written like that by Eratosthenes. Eratosthenes would tell you the following. So pi of x, of course, if you are dividing everything by the prime, the 2 square root of x, you are going to throw out also the prime which are up to square root of x. They are divisible by some prime less than square root of s, and though you are taking them out, so this is not very nice, but it's not that bad. So you have this quantity is, I let some place because I'm going to change that, is the sum when n is between 2 and x. 1 is not a prime number, between 2 and x, and such that the GCD of n and something which is the product. this is not a good notation, but since I am going to use it at the beginning, let me call it like that, is the product of the prime up to square root of x. We'll have some better notation. Later on it will be p of square root of x, but I am using it for some time. So, and px is equal to 1. And so this is what you want to count. Okay? Now it turns out that it may be better to have a sum of all the integers. You'll see that it is more convenient. And so if you add, if I put a 1 here, of course, the number 1 is co-prime with everything. So I am putting a 1 on the first side. And so I have also to put a 1 on this side. Okay, I'm adding 1 everywhere. And it's more convenient. In any case, you may understand that if pi of x is tending to infinity, we have some understanding of what it is. You see, we mentioned already the prime number theorem, which tells you that this is x over square root of log x. So you have the impression that this is very large, so this is p naught and this is p naught. Okay? Already if you have for pi of x something which is as good as this, as an error term, you can jump, you see, and be so happy. So now the point is, how would you detect? So this is something, I mean, with once you have this notation, this is something that Eratosthenes would have understood, and what he was doing, indeed. One, of course, you are counting. Yeah, 1 is here. Okay, so now the point is you have to detect that. How can you detect that something is equal to 1? And we are well equipped to know whether something is equal to 1. Something is equal to 1 when the summation, when d divides m of mu of d is equal to 1. This is equal to 1 if m is equal to 1 and it is 0 otherwise. Okay, we mentioned that for arithmetic function. What we are doing here is multiplying 1, the function 1, at the point n over d, because it is always, the value is always 1. So we are taking the convolution of what would be zeta and 1 over zeta, and you just get the unit for the multiplication. So we have seen that already. So now you have a double sum here, and we exchange the two terms in the sum. We can do for the best. So what is of interest for us, let us call that with a large pi of x or whatever you wish. This will be essentially the thing we're interested in. Don't want to repeat all that all the time, but this is summation. So now what we are doing is, let me do it here. Summation when d divides GCD, or GCD I will just write it like that. Okay, it's not the interval, it's just the GCD. Have some advantage on you that I can recycle part of the things I have written. Okay, and now what we can do? So this is of mu of d. Okay, this is the way we detect the fact that this is 1 if n and p of x are co-prime, and the GCD is equal to 1 and otherwise. And now I change the notation, or I try to save room. The board is not that large. Okay. So this is the summation. So you start by summing over d. Well, since d is going to divide n and px, d may be quite large when it divides px, but dividing n, it has to be up to x in any case. So this is d is up to x, and now what you are saying is that you have mu of d, because it just depends on d in this sum, and now you have a sum over n. So in this sum over n, you are saying one thing, that n is between 1 and x, and the other things you are saying is that n, so of course here you say that d divides px, this is fine, and then what you say is that d divides n. That is to say, if it is a sum of n, I prefer to write it as n congruent to 0 mod d. It is the same thing, but this is a condition on d, and this is because you have introduced n, and this is a condition of n because you have introduced d, but it is the same. Okay? And so this is 1, simply. Okay, you have all the terms are exactly the same just by changing the summation. Okay, so now this is something you know rather well. You have a good expression for that. Let us say that this will be summation when d is up to x and when d divides px of integral part of n over x. This is why I prefer to start at n is equal to 1. It would be a bit clumsy. Sorry? Yeah, d, sorry. Thank you.
You will after x.
Thank you. Okay. So now you have several options. So first option, you expand everything. I mean, you say what is integral part of x over d. This is something which is this. You can say that this is always x over d plus big O of 1. Sorry? And there is some mu d somewhere, right? Thank you. There is some mu d somewhere. Okay, x over d plus big O of 1. So, first option, you use simply x over d plus big O of 1, and then you have something which will be the summation when d is up to x and d divide px of, by the way, this expression is that, but if d is larger than x, this is equal to 0. Okay? And 0 if d is larger than x. So you completely forget about that. We'll keep that later. We'll see what it is. First, we just use this. So we have something which will be x mu of d over d. Mu of d over d, and plus something which is the number of terms you have here, but since you have kept the main term here, you have added. You said it was 0, so you kept it all the time. You have to put it also in the other term. This is the drawback of the first option. We'll see what is the good point on the first option, because then you have something which will be plus summation plus big O of summation when d divides px of 1. Okay, you kept this part, and so you have to take also this part, even if it is to say that this is 0. This may be very small when d is large. This is why it's maybe not a good option. But just to tell you something, what is interesting here, this is fine because you are taking this, and you know that this function is multiplicative, so you can write it as a product. So this will be nice because this is the advantage of the first option. This is the product when p is up to square root of x. You remember that px is the product of all the primes up to p of x of 1 minus 1 over p plus big O. But now here something is very large, because you are taking all the product of the primes up to square root of x, so it is extremely large. So you have something which will be 2 to the square root of pi of x. If you don't know exactly what is pi of x, you can put x, square root of x. For the time being, we don't know what is pi of x, but at most x.
Pi root x.
Sorry?
The square root will come to the pi root x, not root pi x.
Yeah, pi, yes. Yeah, it will be more or less the same, but you're right. It is square root of. No, it is pi of square root of x. Yes. Okay. And essentially, what we can say. So you see that this is absolutely enormous. This is a bit less than x. By the way, we know what it is now using Mertens. You know what it is, but Mertens has nothing to do with the prime number theorem. But in any case, just to know, of course, we are not going to, we were at the beginning of the, not at the Greek, let us say Legendre is at the beginning of the 19th century. So we don't know Mertens at that time. But this, now we know something. We know that this will be something like 2e to the minus gamma x over log x. The 2 is simply because I have a log of square root of x. Okay, and this will come here. The x is here, and then you have 1 over blah blah. Plus something which is, this is extremely large. Let us say it is something like 2 square root of x. And in any case, it's not worse than that. Even if you know that the prime number theorem, it would be square root of x divided by log x or something like that. It's terrible. Okay. Now, what you notice is that when you are doing something like that, even the main term is not the right main term. This is not the main term you expect. You expect something to be x over log x. So definitely, you have many things that occur in this error term. It's not only an error term. It carries also a lot of things. So definitely, this is not a good option. Okay? So now you have the second option. You say, okay, we were maybe a bit stupid to forget about that, because then we have something which will be when d is less than x. Okay? So this will be a correct error term. It will be an error term which is what we can say. We don't know really. Are we able to do something which is really better than big O of x? So this is not that good, and treating this is not that easy. So neither term can be easily treated. Okay? Let us say neither term can be easily treated. So now we have the option of Legendre, which is the third option. The third option of Legendre is closer to the first one, but it is this one. But what Legendre is saying that, okay, let us do something. Instead of taking p of x, let us consider something which is the product. You add some p of z or pz, which will be the product of all the primes. Maybe I call it, because this will be the right notation, p less than z of p. Okay? You change this. What will you get? Well, what will you get if you do something like that with p of z? Then you will get something that you are just taking all the elements which are divisible. You throw out the elements which are divisible up by prime factor up to z. So of course you take z, which is, there is no point to take z too large. Z will be definitely less than square root of x, and even much smaller than that. But then what you get is not exactly this, but at least you have some upper bound when you do that. Because what you are saying is that I am looking at all the elements which are not divisible by 2 or 3. Okay, fine. What you get, all the primes will have survived this process, except maybe the primes up to z. So maybe here you have to put something like z or something like that. But you see, this will be really peanut. It is this which is important. Okay? Because this you can get an upper bound saying this is at most z now, if it is an upper bound you are looking for. So this is not a thing. But now you may be happy, because if z is really very small, then here you get something which will be, this is fine because you have always the product. So you'll get something which will be x product when p is less than z of 1 minus 1 over p. Okay? And even if you have not Mertens with the constant, the first time I was using Mertens to tell you that the first term had not the right order of magnitude, although you have a 1 over log x. But as we know from Euler, this was after Euler. This was at the beginning of the 19th century. So this was after Euler, and so people knew that this was something which was 1 over log z. Okay? Then equivalent to, no, the constant times 1 over log z, because you had to follow the log of it. You had that the sum 1 over p is equivalent to log up to z is equivalent to log z. This we had, if you remember, from Euler already. Okay, and now this, well, you have that d divides n, so you have something which is d is less than x and something like that. And this you can manage now to do something. Well, forget even about that. You remember that this was something that 2 to the z. Okay, 2 to the pi of z if you wish, but even 2 to the z. And you know that you have going to have something which is x over some little thing. But if you take z, which is something like a log with a good constant, boop, this will be smaller than a power of z. So you take a z which is something like a log, but now here you have something which will be a log. Okay? And so this gives you the first result of Legendre, which is pi of x is big O of x over log x. It's not that great, but it's already something. Okay. So maybe I say a few words about some general formulation in this spirit of the sieve. I know I have a big constraint today, that food is, you don't want to miss the lunch. So general formulation. Of the sieve. Okay, let us consider 2 or 3 examples. 2 examples. This would be enough. Of course, you can consider also the trivial example, which was pi of x, but I would like also to figure out something a bit different to try to see what can be the formulation. So, okay, the first is numbers n squared plus 1. Are there infinitely many primes in this sequence? We still don't know it. Okay? But how can we do that? So, we expect that it contains infinitely many primes. Even we have some idea about the number of primes that should be there. One way to do something like that is the following. You see, prime number theorem tells you that pi of x is equivalent to x over log x. It means that if you take randomly a number around x, this number has a probability 1 over log x to be a prime. Okay? So you may think that those numbers are more or less random. They have even a better position. They are in a better position because you remember what we were saying yesterday about that, because they are never divisible by a prime which is congruent to 3 mod 4. Okay? Good. So it has to divide at least the GCD of those numbers, and so it is not. Okay, so we don't know it. What we would expect is even expectation has been given by Hardy and Littlewood. It tells you something that the number of n of 2x, so that n squared plus 1 is prime, this should be equivalent to a certain constant times x over log x. The constant is just for the local distribution among the arithmetic progression, among the primes that don't try to have it divisible by some prime concurrent to 1. But so this takes care in some way of the local distribution among prime factors, okay, among residue classes. Good. So now the Sieve formulation will be the following, that what we are looking at is that this number is the number of n up to x such that n squared plus 1 has no prime factor let us say equivalent. As usual, if you throw away things with small primes, you may take out some of your good friends, but has no prime factor congruent to 1 mod 4, congruent to 1 mod 4 less than x. Don't speak about the prime factor which are congruent to 3 mod 4. We know that they have not. And since the size is n squared, you have to go up to the square root. Okay. So you have a sequence, you have a set of prime factors, and you want to say, I sieve out by those prime factors. Okay? Well, you do the same thing with twin primes. Okay. Twin primes, twin prime or a pair of twin primes as you wish, is a prime number p such that p plus 2 is also prime. Okay, they are very close one to the other. That's why they are called twin primes. Okay, so if you look on the tables, you find a lot of them, even many. I don't know if you look. 101 is a prime, 103 is a prime, 105 no, 107 is a prime, 109 is a prime. So you may have accumulation of primes, so you may also think of finding 4 primes which are like that, and we also expect that this exists, but let us start with the easiest one, twin primes. So again, you can think in the following way. You say, now I know that the probability that an integer around x is a prime is 1 over log x. So you take a prime somewhere around x, you know how many there are, and then you say now, so you have x over log x around this, and now you say, what is the probability that p plus 2 will be also a prime? But you see, for p plus 1 there is no chance, because usually they are all odd, and so there is no chance to have p plus 1, but p plus 2, well, there is no a priori obstruction. So the probability should be 1 over log x, and so you would expect something like x over log x squared. Now be careful, because if you have a prime which is congruent to 1 mod 3, the probability that it is a twin prime in that meaning is very low, because p plus 2 will be divisible by 3 if it is congruent to 1 mod 3. So there are some obstruction, you see. What we may say, attention, there are local obstruction. P congruent to 1 mod 3 implies P is not twin prime, or has no twin big brother. Okay? So, but if you take care of that, you see for 3 it will be important because it is about half of the primes. But if you take something which is mod, I don't know, 101, then this is not very important. only the one which are congruent to 99 mod 101 will not lead to a prime. The other one, well, why not? Okay, so what you put all that together, you can, as we were doing for n squared plus 1, you can expect that the number of twin primes, let us call it t for twin, t of x should be something around c times x over log x, and again square. And again, this constant you may express it as an infinite product, convergent infinite product. Well, if you want to have the value, I think I can tell you c is the product over p of 3 of 1 minus, so then I have to write it by 2. There's the factor 2, which is a bit special. 1 minus 1 over p minus 1 squared. Okay, if you want to have it, this is what you expect. And definitely it works very well with computation. You see, now we can compute things up to a few billion, and so you can really see what is going on. So definitely nobody has doubt that this should be something like that. Okay? But we don't know how to prove it. We don't even know whether there are infinitely many twin primes. You see? Although they are very numerous. You see, something like x over log x, you have much more twin primes than you have squares, for example. It's not something surprising. It's something very common. Okay. So again, what we are going to say, there are several ways to do that, and this is why I want to tell you. One way is to say, okay, what are we looking for? So there are two ways to do that. One way is to look at the set n plus 2, and you assume that those are the n less than x, so that this is not divisible by a prime p up to square root of x or something like that. Square root of x plus 2 if you wish, but I mean this is not really important. Okay? Because then if this number is not divisible by a prime up to square root of x, this is a prime number and this is a prime number, and you're happy, and they both are prime numbers. So again, this is the set you are considering and you are sieving. But this is not the only possibility of doing. Another way to do that may be to consider the prime up to x such that p plus 2 is not divisible by a prime up to square root of x. So you see that you may have different ways to express the same problem in terms of sieve. Tell you something about those two formulations. Okay. So we are going to follow this one first. I say a word on that at the very end. Okay, so now what we are going to do is to look at the general formulation of sieve. The results may be not wonderful, but it is extremely general formulation. So here now, general formulation of sieve. I mean, I'm inside this general formulation. Just a subsection. Okay, so x is a positive real number. Positive real number. A is a set of integers, is a finite set of integers. You remember there's also always the set. Of course, you may consider a very large sequence, all the integers n plus 2, but each time you will say that I'm considering the n plus 2 with n is up to x. So it is a finite set of integers. You say what it is. The P is a family of primes. For example, if you have the formulation which is to look at pp plus 2, where p is a prime number, don't consider the prime 2. It is already out. So you don't consider the prime 2. If you are looking at n squared plus 1, then you are just considering the prime number, which are congruent to 1 mod 4, and so on. So according to the problem, this need not be all the primes. Can be all the primes, it need not be always all the primes. And okay, and z is an integer which is at least 1. Okay, so we are going to, in some way, to use p of z. This is what we are going to look at. We are sieving by the primes up to z, and so we look at the product of the primes up to z which are in p of p. This is the factor we'll have. This is not surprising with what we have been doing up to now, of course. Okay. So now we let s, let us say 0 or s usually of APS, this APZ is the number of prime. This is the number of elements in A which are coprime to P of Z. This is what we have been doing, even if Legendre, well, we had something which was all the element A were up to X. For the time being, X does not occur. I will tell you where X occurs. You have all the element up to X, and you are saying, okay, I'm just considering the prime up to square root of up to log X or something like that, and then I'll be happy with that. Good. So what is important for us is to say we have the shifting function. So the shifting function, you can write s of 0 a p z. Well, then you count the number a up to a of s0 of a. And what is s0? I write it in the same formula because this will be fine. This is in the same formula, summation when d divides a pz, the GCD of a and pz, and this is mu of d. Okay. Indeed, this shifting function is 1 if d of a pz is equal to 1, 0 otherwise. Okay, but I prefer to write it in that way for the time being. So this is exactly 1 if you are in this set and 0 otherwise. So this is why you have this inequality. And this is just the one we are used to use. Okay? So now, of course, we are going to shift the summation, as we usually do. And so what we have to consider, so this will be the summation when d divides p of z. We are thinking of Legendre and say maybe we take a p of z which is not too large. And then this will be the sum now when a, of course you have the mu of d here, and then you have a in a, and a congruent to 0 mod d of what? Of 1. Okay? So this is something you need to have some information of that. This is what you say. If I want to sieve, I better have some information of the distribution of the element of A in the arithmetic progressions. At least the interesting arithmetic progressions, which are the D, which have only prime factors up to Z. Fine. And since you have mu of d, you are just looking at square free number. There is no point to look at something different. So this is what you need to have is the following. What can you say about this number? So x has not occurred up to now, but x will occur now. We make some hypothesis that we expect to have a relation of the type AD, let us say AD, will be this sum, the cardinality of AD, if you wish, I write everything, and this will be the number of elements. This is this number. This number I call AD. Okay? And this set you can call AD with a curly A. And what you expect is to have something which tell you that this is now you have to say if x over d, this wouldn't be that great. For example, if you are thinking already of twin primes, because you have to select two, in general, two values, mod prime p, because you want to say that n is not congruent to 0 mod p, but n plus 2 is not congruent to 0 mod p. Okay? So what you exclude is indeed two elements. For those for which it will be 0 mod p, you have to suppress two congruent classes, mod p. Okay? And now, since it is congruence, usually you have the Chinese theorem, which will tell you that this function should be a multiplicative function over d. Okay? If you are looking at the primes 2, this will be different, because for the twin primes, then you will have to say, okay, as soon as n is taken out, then n plus 2 is also taken out at the same time. So your function will be just, you see one class mod 2, but you see different class. So what you expect is to have this number, which is something which is essentially x over fd. This would be the number or something like that, plus a remainder. You expect this to be a remainder. So this is just in sort. This is nothing. You have to say, I choose my multiplicative function so that it corresponds to the problem, and this is a definition of the remainder. Of course, then you expect that you have something on the remainder, that what you expect is that this, where f is a multiplicative function, and RD is expected to be a remainder term. So,
put the x on the data.
Sorry?
The x data is missing here.
Some x is missing somewhere.
Where does it put x?
No.
No.
No, sir.
No, up to now I have not introduced x.
Now what is this AD?
Sorry?
What are you counting?
I am counting this number, the number of elements in A. So this is to say that x is something which is associated to capital A. But in some cases, it will be the number of elements of A. But in some cases, it will be maybe x over log x will be the number of elements to x. For the time being, this is true. I have a finite sum. You see, I am not cutting a sequence, but if I am cutting a sequence at x, then I will have something where x occurs. Okay? This is just a sequence, and of course this sequence will be connected with x, and this is the way I expect it is connected to x, that there will be a relation of this type. This is something we have seen in the case of twin primes, in the case of n squared plus 1, in the case of primes themselves. We know that we have something like that, but I said simply A is a finite set. I don't want at the beginning to say that A is connected with x. A is connected with x, but in which sense? This is exactly the sense in which A is connected with x. What I expect is that each time when I have my finite A, I can find a relation of this type. Okay? So I didn't say a priori that A was something. If you have a finite set, this will be always okay. You see, for all this part, you don't need to put some x. There's no x here. When I am taking all the n up to x, then okay, this will be my set A. But it will not be exactly the n up to x. It can be the prime up to x. And if I take the prime up to x, then this number will not be x any longer. It will be x over log x. Okay? So this is the way A is connected with x. If I want to be too precise at that level, then I am in a slightly messy condition. But of course, you understand that if you have something like that, for 1, you will get also something which tells you that AD, A1, which is A, is x plus a remainder. This is true for all D which are of the type for D, for D dividing pi of z. Maybe I should insist there. So for 1 we have A1, which is the cardinality of A itself, because if you say that the element of A are congruent to 0 mod 1, it's not that you are speaking of integers, and to say that an integer is congruent to 0 mod 1, it's not a question of uniform distribution mod 1. It's not at all uniformly distributed, it's all the elements. And so what you expect is that you have something like that. So x should be the size of x, the size of the element of A. Okay? It need not be exactly x, but it can be also something a bit different. Is it fine? Okay. So now this was S0. So now you have this for AD. Well, you plug it in this expression, and you have S0. So we have S0 is equal to summation when D divided Pz of mu of D, and then you have this sum, which you know is x over Fd plus Rd. Okay? And then you are happy with that. You know what it will give you. You will get something which is x. In the first term you have an x which goes out. And then you will have the product when P divides Pz. Because mu of D over f of D is a multiplicative function. Okay? So you have Euler product, and this will be 1 minus 1 over Fp. Okay? This is why you prefer to have Fp which is non-zero. The primes which do not occur in your problem, you better not put them into it, otherwise you will have something which is, you want this factor then to be 1. And it's not that easy to express, so it's better to suppress the term which do not occur in the business. Plus, then now it will depend how it is. You may keep this error term explicit, because if you have to combine it with something different, never put an absolute value if you don't need it. Let us say that you have something which will be d over p divide pz of mu drd. Of course, you understand that usually what you are going to do is to put some absolute value here, but I prefer to leave it like that, because in some cases don't do that. And this was really the big success of Henrik, of Ivanets in the late 70s, was really to take something which is something like that. Okay, so this is in some way the general way of seeing the sieve. And of course you try to take Z. You are inspired now by Legendre, and you say, okay, maybe I don't find the best Z which will completely solve the problem, but maybe I can get something out of this. Fine. Well, now there is also something that is interesting. And I say this is a zero because this is exactly, I mean, this is an equality here. Okay. So now the point is to try, and this is the great idea of Brun. Viggo Brun was a Norwegian mathematician. Brun's first combinatorial sieve. It is simpler, it already gives some very nice result. You can do better, but it's more complicated on the combinatorial side. So let us do, well, what is the time you want to go to eat? 1:15 is really the limit. Because we have still 1 hour. Okay, so now you can do the following. Replace S of A, S0 of A, by any SA. So you remember that S0 of A, well, I erased it, but this was the summation when D divides APZ, D divides APZ of mu of D. Okay, what you do is you take a very general form and define blah 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 in the same way. S of APZ, you'll see why it is useful. So this depends on S. It is not the S0 which is for the value mu. It is for any function which is expressed like that. You can do the same business and write the following. This is the summation A belongs to A of SA, and this you exchange your thing, you exchange everything, and this will be X summation when D divide P of Z of lambda D over mu D plus, I have not yet gone to the product, so you need not say that this function is a multiplicative function. Okay? I am at that level, and that level I have not used the fact that mu is a multiplicative function. I'm exactly at that level, plus some summation when D divide P of Z of lambda D RD. This is formally the same thing.
In the main term, you have lambda D by FD, because you have not still proved FD.
Oh, yeah. No, it is FD. Yes, it is FD, of course. No, it's mu which is replaced by lambda. Yes. Thank you. So it is exactly the same formulation. I don't go to that because I am not asking that it is, but this is nice. I should be able to say something about this term. You see, usually main term is not where comes the problem, as usual. The evil is in the details, or you say something like that, no?
Yeah.
Yeah. Good. Well, now the point which is interesting is that what you want to have is, can we try, could one get some functions lambda such that I'm going to call them SA is, in the first case, is S plus of A. That is to say something which is always larger than S0. of A. Is it possible to find something like that? Then you will get an upper bound for what you are looking for. Okay, suppress that, but I will say that this sum, if for all SA is always larger than that, then I will get an upper bound for a 0. Okay, or SA is a minus function of A, that is to say a function which is less than S0 of A. And then I would get a lower bound for it. Okay? So, well, this is exactly what Brun is doing at first, but the nice following thing. I don't know exactly when it is. I think it was around 1915, but I would say around. I'm sure that here I'm not taking too many risks, with too much risk with that.
Definitely between 1910 and 1920. Between 1910 and 1920.
Yes. Yes. So this is circa. It is up to 5 years. No, it was before. It was before 1920. This is sure,
yeah.
But I don't know exactly when it was. Because okay, so let 1t denote the indicator. Let 1t denote the indicator function of the integers n such that omega of n is at most t, and I see now that I have not defined what is omega, the function omega of n. So it is an arithmetic function. Everything is an arithmetic function, as you know. So omega of n is just the number of primes, of distinct primes you are in n. So this is when p divides n of 1. You can see that, by the way, this is an additive function in the way that if you take two integers which are coprime, then omega of n of the product is omega of n plus omega of n. Or if you prefer, if you take something 2 to the omega of n, this will be a multiplicative function. Okay. So the omega of t, then, well, this is just a definition, then for any integer h positive or 0, the function lambda I of d, which is mu of d, times this indicator function. Now you are taking the mu of d, either mu of d or 0. You are keeping mu of d if d has a number of prime factors which is less than 2h minus 2 minus y. So this is for I is equal to 1 or 2. What it means that, if you take I is equal to 1, this is an odd number. If you take 1 is equal to 2, it is an even number. Okay? So the function, this function, is a multiplicative function. For I in 1 and 2. So I am covering essentially any value here. Any value can be written like that, but if I isolate I, it's just to say in one case it will be odd, in the other case it will be even. This is the only point, like that. So I am truncating in some way the values of the divisor D. I am putting a 0 if it has too many factors. But I am clever at the point where I stop after an even number of primes or after an odd number of primes. And what is interesting is that this is a multiplication such that, and this is what is our good business, is that lambda 1, this is when it is odd, lambda 1 convolution product with 1, that is to say the sum of lambda 1 of D, is less that mu convolution 1, and this is less than lambda 2 times 1. So it is a good way to say that, you see, we are always summing things. I mean, instead, you see, in the sieve, instead of putting mu, which we know how to do with a general lambda, if we take for lambda something which is a lambda 2, we'll get an upper sieve. If we take something which is like a lambda 1, we get a lower sieve. Okay? So this is not too difficult. Now we have to understand how we manage to deal with when we cut, saying there is an even number and an odd number of primes. And this I would like to do it for the twin prime problem to understand how it goes. So we have to prove this proposition, and essentially you just have, should I write? Yes, it's easy. Okay, let us prove this proposition. Okay. So first, when you are, so what is lambda I? Lambda I take only one of them. No, I don't need two. Lambda I times 1 of n. This is the summation when D divides n of lambda I of D. You see, this means that it is times 1 of n over D, but this is just always equal to 1, so there is no point to write it down. So this is fine, you have this. And I have to show that this is either larger or smaller than the same sum with mu. First of all, this depends only on the, you see, the D can be always assumed to be square free. So this only depends on the kernel of n, so you can assume that n is square free. Okay? So we assume, we let, without loss of generality if you wish, we let n to be p1 blah 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 pr. Okay, there's the product of primes which are pairwise different. Okay, so now let r, no, sorry, I wrote it with k, I prefer to go on like that. For any r, there are k choose r, divisors, r choose k, you call it, it makes some more sense, no? Divisors of n with omega d is equal to r. Okay? So for any t, we have the following: mu times 1 t times 1 of n. I tell you what it is. This is the summation of UD when D divides N and omega of D is at most T. Okay? So you can write it in the following way. This is the summation when R is at most T of mu D, and for each R, then you know what is this number. This number is minus 1 to the R. You select it, and you know when omega of D is equal to R, you know exactly how many you have, but there's also power in that. So this will be minus 1 to the R times K choose R. No, you write that. Okay? You know how many there are. You have counted the number of elements, but you know that the mu will just depend on the number of them. So this is that, and if you compute this correctly, you will find something which is minus 1 of T, and this is K minus 1 choose R, choose T. This is some computation. You are old teaching, or you're a postdoc, or you have some first year students, so you ask them to prove that for you. Okay. And this is fine. This, I mean, by induction you prove that, and you are very happy because you get exactly what you wish, that is to say, whether it is positive or negative. And this is usually when D divides N, you have to compare with this, which is only 1 or 0. So when D is equal to 1, there is no problem. Whatever you do, you always get a 1. And for the other value, either you get something positive or you get something negative, and you are happy. Okay? So this is fine, because you see, you can just select, maybe I can choose, I can stop at 2 elements, the numbers with at most 2 primes, and boom, I am an upper bound or a lower bound in the sieve. Well, they may be, of course, a bit stupid if you stop too quickly. This is the problem. But at least this is very fine, because you see you have something which is quite reduced. Because if you have Z and you don't want to have a big error term, if Z is something, let us say that x to the 1 over 10, then stop at 10 and you are happy, because your error term will be good. Okay, this is the problem. So let us write it now to be happy with that. Private fun theorem. So this is Brunn's first combinatorial sieve. Now you understand that even with the mu function, you may do things which are a bit more elaborate in the combinatorial construction, and this is the point. But already with this, so let A be a finite set of integer be a set of prime, as we have in the sieve, but I want to tell you what it is. Again, for D larger than 1, we let AD to be, as it is usual, the number of A in A, such that A is congruent to 0 mod D. 0 mod D. And for Z, we let P of Z, which is the product P in Z, P up to Z of P. Then for any H positive, we have the following, that S of A S0 of A P Z is less than summation mu of d AD when d divides P of Z. There's nothing new in that, but it's better to have it if you want to use it someday. Better to have it written like that. And summation when d mu d of AD and d divides PZ and omega of d is at most 2h plus 1. Okay, it is just the parity of the number of prime factors you are choosing, which permits you to have something which is upper bound or lower bound. Well, this may be not also the thing you are really interested in, because maybe the Z will be too small for getting exactly the number of primes. We're already integrated here Legendre, because the condition we'll have for A is something which is not in Z but in H, and there will be this parameter Z. Okay? But maybe if the thing is going to work, and it is going to work, the point is that we shall be able to get a Z which is much larger compared to X than the Z that Legendre was using. You see? Instead of having a log, maybe we have something which is closer to a power. Okay. So, next section is really the twin primes, and I would like to show how it goes and to give you Brun's first upper bound. So theorem, again I don't put a date. I think it has been published. This was published in 1919, but when he was introducing all the business is not completely clear, and I couldn't get from him some precise dates. He was over 80 when I met him, so I didn't want to bother him too much. We had some nice tea and that's it. As n tends to infinity, one has, I already called it Tx, maybe if you wish I recall that, is the set of Q less than X such that Q and Q plus 2 are prime. This is big O of, so you see what we were expecting is to have X divided by log X square. Divided by log X square, but there's something which is not that great in front of that, which is a square. Okay? So obviously Brun understood that it should have been log X square, he had no doubt about that. But this was not really great, but at least you have a corollary. Which says that if you take the sum of 1 over q, when q is or q plus 1 over q plus 2, whatever you wish, this is not a problem, where q plus 2 are twin. This is the same thing, it's just 2 times the sum, you don't care much about that. This is convergent. You see? And if you think that you want to do something like Legendre will be doing, Legendre would have been able to do something that maybe not exactly Legendre, but possibly Brun. You need to know more about the distribution of prime. But if Brun were using Legendre, simply he would have got something which is t of x is less than, so there would be x over log x, this is for the prime, and instead of getting an extra log, he would get a log x. And you see that this is a divergent integral or sum on the integer, just at the limit, you see. When you integrate that up to t, you get something which is log t. Okay, so you need really to do something more. I mean, this is just integration by part. Okay. Fine. Okay, yes, we have time to look at that. So let us prove it. I think we have time to prove it. Okay, so of course we are using Brun sieve and we are taking A, which is mm plus 2. M is up to x. This is where you see in the definition you put x. For the finite sum, you are here is an x, because this will give you the right way for computing AD. AD will depend on x, and we have the right thing. Okay, P, the set of all primes. You see, we are not taking P, the prime P, and P plus 2 for P up to x, because the remainder would be something complicated with prime in arithmetic progressions. And this at that time was not available. I will tell you when it became really available. Okay? So for z 1 less than z less than 1x, we have the following, that t of x is at most z plus, but you see z will be less than, really less than x over log x squared. It will be even much lower than that. So this is not going to be something bad, but it is just, you see, when you are sieving the first term, you are throwing them away, and they should be in the business. But so this is nothing. Plus, and what is important is that this is S of A, B, Z. Again, like in Legendre, if you are sieving by something which is too small, well, you can say that what will remain are not exactly the one you wish. There will be some other which will remain because they are divisible by a large prime. You are not sieving with this prime. You say, okay, this one is going to stay in the business. Good. And so this is at most, and now I write it that way. It is, as usual, d divide p of z, but what I say that omega of d is at most 2h. Okay? Need to have 2h, because then I am sure that I have an upper bound. 2h of mu d Brun is using the mu. He has not changed the value completely. I said in the general feeling you can put a lambda. No, what he said is simply it will be the value of mu when d has a certain number of primes, otherwise it is 0. But it is that what he is saying. AD, let us say plus z if you wish, but don't forget about the z. Okay, so what you have to understand is what is AD. What is AD? AD is the number of solution. AD is the number of a solution with m up to x, the number of solution to m plus 2 congruent to 0 mod d. this is nice. Chinese, it is a polynomial congruence, so Chinese remainder theorem tells you that it is multiplicative. Since you are interested only in D which are square free, you just have to know for each prime how many solutions you have here. Of course, this number of solutions, if D is equal to 2, you have exactly one solution. Fortunately, if there were 2, you would be in a well, difficult situation. You have one solution when P is equal to 2, and for the other one, you have 2 solutions. Okay? So you have a function, let us call it rho D if you wish. Number of solutions. So maybe it is not in the denominator, now it is in the numerator, but it's the same thing. So the number of solutions, and m plus 2 congruent to 0 mod P has, I mean, in general, m up to P has one solution if P is equal to 2, and 2 solutions if P is larger than 2. Okay? This is the number of solutions of this congruence. And you write, let rho be the multiplicative function such that rho of P is equal to 1 if P is equal to 2, and is equal to 2 if P is larger than 2. Then you know what is AD. Then AD is equal to X, because you are counting the number of elements up to X, so it is X, and it is rho of D divided by D. This is my F function, or 1 over F function as you wish. X rho of D over D plus, and then you have a big O. You see, what you are doing is that when you are counting the number of terms, you are taking exactly a multiple of D, and then what remains is at most rho of D. In the remaining term, it is an interval of length than D, and in this one, maybe all the solutions are here, or less, or none, you don't know, but it is rho of big O of rho of D. Okay, this is just ordinary mathematics. Okay, yeah, it's fine. So you remember what it is, and I write it here. AD is equal to X rho D over D plus big O of rho over D. Fine. So Tx is at most X. So the main term, we know what it is. It is the sum when D divides Pz, when omega of D is at most 2h, of mu D rho D over D plus big O of something. This something will be Z. Forget about Z, because this is really not, as I told you, a problem. What is important is that this will be the summation when D divides Pz and omega of D less than 2h. You see, we have two parameters at our disposal, Z and h. X is fixed because we are looking in one interval, how many there are. We cannot do much out of that. And so this will be rho D over D. Okay. So I am not to write everything at the same place. Okay. So what I am going to do here is simply in these things. I like, you see, to have this Euler product as a main term. Yeah.
So, the denominator is the vote out.
What? Ah, it is row. It is row alone. This is what you mean. Yes. Yeah. Yeah. Thank you. Yeah. So now, first we are going to use as the main term the full term. So we'll see later on what we are going, or maybe we can do it right now. Okay, so main term, we want to erase that. So of course it will mean that there will be some term that will go into error term, the one for which omega d is large. Okay? So then we have, I start by telling you what is the main term in some way, how you can compute that. I forget about this condition, mu d, rho d over d. Well, then you are quite happy with that because this is an Euler product now. Okay, so this is the Euler product. So you have when d is equal to 2, it will give you some 1/2, and it will be easier to put something which is the product when, forget about the prime t, p2 now, this is 1 minus 2 over p. You see, because this is not the same value. You have the value 1 for 2. And if you have the value 1, it means that you will have something which will be 1/2. And this 1/2, I don't write it on the general way, I just write it here. Okay, there's nothing. So, okay, so you know what it is. And so this is less than something. How to write it if you want to know this is less than 1/2. Let me write it as a product over p over z. Well, when you have something like that, this is important, and what you know is Mertens. So if you want to go through Mertens, what you do is that this is 1 minus 1 over p square. And then there will be something which is the product, which is absolutely convergent, but if you are interested only in a upper bound with no idea about the constant, forget about the constant, you just say that this is less than 1 minus 1 over p square. Okay? This is fine, and it's better even to put all the prime value here, including 2. And of course, for the prime value including 2, then you are adding something which is a bit too small, but it's not a problem, you put the factor 2. Okay? And then you know what it is. And this is equivalent to a constant time 1 over log x squared. This is equivalent to a constant. You know what is this constant, but you don't care about the constant. What is important is that it is log z squared. So you see, this is important because you understand immediately that what you get is something which is x over log z squared. So if z is rather close to x, you will be happy because you have really a main term which is x over log x squared. And you have a good margin not to go too far from a log x because you have a log here. So if you have something which is somewhat close to x, you will be happy with that. Well, if you have to take it a bit larger than a constant or a bit smaller by some log itself of x, you will be happy. This will be the main thing. So by the way, the log x squared over log x squared comes exactly from here. You understand what will be our z, so that you produce the log x squared, but you miss a tiny bit because you cannot take that to be just a constant time log x. In some way, it cannot take z to be a power of x. It has to be something smaller than a power of x. Okay, you are not dealing with almost primes, for those who know that. Good. Let us go to the error term. Of course, don't speak about the error term z. You understand already that if z is going to be something that that is a small power of x, you are done, and it will be even smaller than that, we stop about it. So there are two error terms. There is this error term and the error term which comes from here when you complete the sum. Okay. So what is the easiest one will be the error term which is here. So now we have sum of rho d. D divides P of Z, and omega d is less than 2h. Well, so what you know about rho d, since you have omega d is less than 2h, and rho each time you add a factor 2, so this is at most the summation when d divides pi of z and omega d is less than 2h of something which is 2 to the 2h. Okay? Each of the terms you have a factor 2, but the number of factor 2 you have is bounded by 2h. Okay? So essentially you have just to count that. But you have to count that, and what is this? This is just the number of primes up to z. You are just dealing with prime up to z.
But you have taken care of omega d is less than equal to 2h because you have multiplied it to the power 2h.
Sorry?
You have put a upper bound for rho d as 2.
Yes?
And omega d is less than equal to
No. Sorry. Rho d is 2 to the 2h.
Oh, d, okay.
Rho d, because for each prime
Yeah.
you have a 2,
Yeah.
but the number of prime is bounded by 2h. So, okay? So this is rho d is really 2 to the 2h. I have not changed anything else. Okay? Now you have the number of divisor where you have this. How many primes you have? Well, the number of primes is at most z. You have to understand that really the number of prime up to, it's maybe z over log z, but you understand that the z over log z, if you have something like that, the log you are going to add will not make you win anything. You can lose it for free. Okay? So this will be something like you have P of z is the product of z terms, and in the z terms you are choosing something which are h term. And so this is at most, or maybe big O, but possibly this is fine too. And this is at most. I think this is fine to write it like that. This will be z2 to the 2h, and this will be z to the 2h. Number of possibilities you have, and even I am losing some choose function by some power, but it's not all that is not a problem. So this is something which is in some way a big O of, as you wish, I don't know. It is at most 2z to the 2h or something like that. Okay, I'll see what I have to do with that later on. But what I need is to say that this error term, the first error term, this I have to choose h and z so that this is less than x and even a bit less than x. Again, winning a tiny bit for that. If it is x, you are happy. You just have to change something which is not too bad. But I would like to go to the other error term. Okay, so first error term, you remember that this is, maybe I write it here, O of 2z to the power 2h. Yeah, it's fine. So you have the summation when d divides p of z and when omega of d is larger than 2h of rho d over d. Well, fortunately, we have a d at the denominator. Otherwise, we would be in a difficult condition. Okay? So now we know that omega of d is larger than 2h. And essentially, you have something which is a weight which is 1 up to this, and which is 0 afterwards. And this is something when you have something like that, a 1 and a 0, and you want to get an upper bound by something which you can handle in some way that you can manage. If you, I don't know if you have seen probability and you know Chebyshev inequality. Chebyshev inequality is exactly that. You have a function which is 1 or 0 and you take an upper bound of this function. So here you have to take a nice upper bound, and you say the following, that if you are looking at this, if you take you consider, let u be a parameter, anything, it will give you some room for choosing it, but the choice will be take something 5, 6, 10, this will be the same thing. Then if omega of d is larger than 2h, we have rho d is less than u to the 2 omega d minus 2h. I think this is fine. Okay, let us see how it is. If omega d is less than 2h, this is something which is positive. So you're happy. If ud, no? This is always positive. It's a power. It's always positive. Now, if you assume that omega of d is larger than 2h, this is, if omega of d is larger than 2h, yes, then 2 omega of d, so omega of d is larger than 2h, 2 omega of d minus 2h is larger than 1 of the omega of d you keep, this is very important, and the other one you say it is larger than 2h, so it is larger than omega of d. Okay? And so this is, and u is larger than 2, so this is less than 2 times omega of d. Okay? And I put it that way, this is less than 2 to the omega of d, and this is correct. Okay, rho d is less than, I should have put it in the other way around. Rho d is less, now I put in between 2 to the omega of d, and 2 to the omega of d is less than this one. Okay? Well, you are happy with that. So now you just have to compute what it gives you. Okay? So then, again, now you forget about that. Once you have put this upper bound, forget about it and sum over everything. And again, this is multiplicative function. I mean, you have the factor u to the minus 2h, but beside that it is multiplicative function, and so you can write it through an Euler product. So this is summation blah blah blah. I write it here. This is less than u to the minus 2h. Okay, this is the factor which is here. And then I have something which will be the summation of rho d, which is u to the 2 omega of d, divided by d. And this is when d divides p of z. And I can get rid of this condition now. I get rid of this condition because I want to have an upper bound. Okay? So, fine. So now this is u minus 2h, and it is Eulerian product. P is less than a z of something which is 1 plus u2 over p. We have done the most difficult part in some way. So now you are happy with that. Maybe I will recall the major part is this. what I say is x up to a constant, it is x over log z square plus 2z to power 2h. I think this was to power 2h that we had, plus another term now, which is this one. Okay, I have everything here. Yeah, I think I have all the other term. And so I can go on with this one. Again, this one, you said that this is the exponential of something, so it is the exponential, or big O if you wish. You don't care much about the constant. It is big O of what? Minus 2h log u. This will be a constant, u. Minus 2h log u. This is important simply that it is larger than 2 to recover the rho d. And then you have something which will be plus, and this will be something, again, you have this u square, so you may consider that this is 1 plus 1 over p to the power u square. Okay? So you will have a u square times log z. Fine? Yes. So what you do is the following. You fix u. I don't know what is the best value. Put 10, but anything, any constant sufficiently large, you have to work a bit out of that. But you see, you have some. So this is a constant. And this is a constant, so this is large, but you would like this to be negative because you want to have an error term, okay? So you would like to have this. So now you have the possibility of choosing h. So you choose h such that this is bigger than this. So this is a constant, log u is a constant, so essentially h has to be something which is larger than a constant times log z, okay? So h, you find it to be alpha log z. So you see the number of primes you are considering is somewhat large. You don't stop after the number having at most 2 primes or something like that. H is log z, and then what you want is to have so that this expression is at most, this is at most log z to minus 3 to log z of minus 3 or something like that. Exponential, no, let me write it correctly. Yes, so that this exponential is at most exponential of minus 3 log z. And this is at most log z to power minus 3. Okay? So you remember that there was always a x which was in front of all the business, and we have not looked at this. U to the minus, yes, it is done here. Okay. So what is the problem? No, I have. I think I was a bit quick in doing that.
No, it is perfectly okay. For this choice, you have to now prove the 2z power 2h is small.
Yes, yes, but z has to be a bit. H has to be large, and if h is too large, I think this is fine.
This is fine.
I think this is fine, and then you have to check that So this last term is fine, but then you have to do something with the z to power 2h. Yeah, and this is where you have to choose what is z now. Okay, so this was regardless of z, and now I have to choose z so that this one is not too large. So then you have this one, which is something which is exponential of 2h log 2z. So you have something which is a log z, and what you want to have is log z times log z should be something that less than, and then there's really no problem. Now you can take whatever you wish. You can take x to 1/2, you can take anything, any power, because this is just a constant you have here. And this is how you find to get this. You get something that log z, so you choose log z to be something which is a constant times a small constant times log x over log x. And then since you had a log z square in the denominator, you have a log x. So okay. So there's just one thing I wanted to tell you. So there's a fundamental lemma. Fundamental lemma tells you in some way that by Brun-Sieve, you can always consider you have a sequence. You can say, by the way, the small primes are not important. I don't lose too much in saying I don't want to be bothered with the small primes. I can take the small primes out. Okay, and it will remain something. I have some equivalent for what remains, and this is what we call the fundamental lemma. There's one thing just I want to tell you, because it's 8 and so time is running, for approaching the problem. So you see, if you say, for example, well, if you are a bit in a bit better situation, you will say, okay, in my sequence n plus 2, I can take out all the prime factors up to n to 1/6. Good. But if you want to have a lower bound, again, you are going to lose something, but you can say, oh, if I take all the primes up to, I'm looking at n plus 2 with n around x, I am taking out all the prime factors up to n to, or x to 1/6, and there remains something. What can I say about what remains? Well, if n has no prime factor which is smaller than 1/6, then it means that n has at most 5 prime factors, even with multiplicity. So what you can say in this, and this was the second part of Brun, because with that you cannot say it, you need to have a constant and not the log. But if you have a constant, you say, okay, then you can say that there are infinitely many integers n, such that n and n plus 2 have each at most 5 prime factors. So it's not the prime, but almost primes. Now you know also that Chen result in the mid-60s was to say that there are infinitely many prime p, such that p plus 2 has at most 2 prime factors. So you don't get it with n plus 2. You have really to use the fact that you start with a p. And so you need to have something about the distribution of primes in arithmetic progression. And distribution of one prime in arithmetic progression is something which is not that great, because really it depends on the you expand the L functions. You see, with the Dirichlet character, we almost touched these L functions, and but then you expand it and you go into the complex plane, and you find a region without 0, and for each one it's not that great. For example, even for prime numbers, you don't know something telling you, for example, that the Chebyshev phi function, which is the best function, you would expect that the error term in the phi function is x to 1/2. We don't know anything like a power. But if you are looking at the mean value in means of the distribution, then you have something which is very nice, which is something which has been proven independently by Bombieri. So it is a bit outside this, but this is really something to know. Theorem of Bombieri-Vinogradov. I should really write Bombieri, Enrico Bombieri, and AI Vinogradov. It's not the same, and they are not in the same family of the one who proved that every sufficiently large odd integer is the sum of 3 primes in 1933. This was in published. So they independently published the following, that we have, I don't want to tell you something too stupid, so let A, there are several ways to formulate it. Let A be positive uniformly in Q and X. One has this is really the average of the Euler term of the distribution in arithmetic progression, Q up to capital Q, and you take the maximum when y is up to x, the maximum when A and Q are co-prime. Of course, if A and Q are not co-prime, don't try to find too many primes in an arithmetic progression A modulo Q. And then what you are doing is you are taking phi in absolute value of yqa, which is what you expect. That is to say, not exactly the number of primes congruent to A mod Q, but this weighted with the von Mangold function. Okay, minus A over Q, y over phi of Q. This is what you expect. That they go up to x, and yups. This does, yes, psi is good because you don't have the lambda factor. The lambda is here, so it's fine. This should be well distributed. Now, if you are really thinking, oh, I know that because this is something like square root of y or something of the kind. If you have something that would tell you have an error term in square root of y, then the maximum would be something like x square root, and so you should have something which is q times x 1/2. Okay, this is what you say if I have this. And by the way, this is true. This is big O of x over log x to the a. Okay, this you can do something like that. Plus, and if you are looking at q, this will be x 1/2 q times log x3. 3 can be replaced by something else, but this is not important. But essentially, you see, if you know Riemann hypothesis, general Riemann hypothesis for all n function, and you use it here, you don't get better than that. So it's very useful. So now, if you deal with that, and you are tackling the problem of twin primes, better consider them as p plus something, having at most a certain number of prime factors. And about that time in 1966, Changing Run, proved that every integer can be represented, even integer can be represented as the sum of a prime and an integer having at most 2 primes. So we're really at the end, except proving that it is the sum of 2 primes. Okay? So I think, yeah, 1:15, we stop, we rush to food. Okay, thank you very much.